The metal breaks chemistry's rules. The solids become one liquid. No flames, no obvious reactions. Curiosity reveals hidden atomic mechanisms. Every mystery has explanations inside. Gallium challenges familiar metallic behavior. Science uncovers astonishing hidden truths. 5 mysteries drive this investigation. Chemistry replaces myths with mechanisms. Let's begin exploring gallium together. This investigation explains surprising chemistry using evidence instead of entertaining trivia. Every mystery reveals mechanisms hidden beneath ordinary observations and familiar expectations today. Gallium sits beneath aluminum within periodic table group 13, surprisingly together there. Aluminum melts extremely hot, yet gallium melts inside your warm hand easily. Scientists long considered gallium's melting behavior an unexplained chemical anomaly for decades. Atomic structure finally revealed why gallium behaves unlike ordinary metallic elements completely. Most metals contain closely packed atoms sharing freely moving delocalized electrons together. Gallium instead forms unusual crystal structures containing paired covalently bonded atoms first. Each gallium atom strongly bonds one neighbor before weakly connecting surrounding atoms. Researchers describe gallium as molecular metal, unlike nearly every other metal known. Gallium combines combined characteristics alongside traditional metallic bonding behavior simultaneously together. Solid gallium contains billions of tiny gallium dimer units throughout crystal lattice. Gallium's melting involves breaking paired dimers into independent individual atoms completely everywhere. Melting occurs because entropy dramatically increases during dimer separation into monomers instantly. Disorder makes melting thermodynamically easier despite relatively strong covalent atomic bonding remaining. Gallium melts because increasing disorder outweighs bond-breaking energy requirements significantly instead. Gallium's paired atomic lattice eagerly transforms into more disordered liquid arrangements naturally. Understanding gallium's structure unlocks another remarkable mystery involving liquid formation immediately afterward. Solid indium remains stable until mixed directly against solid gallium at room temperature. Rubbing both metals together creates unexpected liquid without external heating whatsoever involved. Liquefaction occurs rapidly only through contact, friction, and atomic interaction together alone. This surprising process represents phase behavior instead of chemical reaction entirely here. Eutectic phase diagrams explain why solid mixtures liquefy unexpectedly under ordinary conditions. Mixed atoms struggle arranging themselves into orderly crystalline structures during cooling processes. Foreign atoms disrupt crystal organization, making liquid arrangements energetically more favorable overall instead. Maximum disruption occurs precisely at eutectic composition, lowering freezing temperatures dramatically together significantly. Gallium and indium randomly distribute atoms throughout liquid alloy structures completely naturally. Entropy of mixing actively stabilizes liquid state through thermodynamic principles operating continuously together. Gallium-indium eutectic alloy remains liquid below ordinary room temperature conditions with stability. Adding tin creates Gallinston, lowering melting temperatures even further below 0 degrees. Gallium's entropy-driven melting combines with eutectic disorder, creating remarkable liquid stability together permanently. Liquid stability results because crystallization becomes increasingly difficult after atomic mixing occurs. Preventing orderly organization explains alloy persistence without continuous external energy input required. Same principle later explains gallium damaging aircraft-grade aluminum from inside unexpectedly too. Aircraft aluminum normally combines impressive strength with excellent ductility under mechanical stresses applied. Coating aluminum using gallium dramatically weakens structural integrity within minutes under heating. Gallium causes embrittlement without dissolving aluminum through ordinary chemical reactions occurring ever. Aluminum contains microscopic grains, separated by naturally disordered boundary regions everywhere internally. And externally, gallium penetrates damaged oxide layers, entering vulnerable grain boundaries extremely rapidly thereafter. Diffusing gallium weakens grain cohesion, initiating cracks before catastrophic structural failure eventually. Gallium enrichment along boundaries reduces cohesion between neighboring aluminum grains significantly together. Microfractures begin forming before linking into complete structural failure under applied stress. Gallium exploits structural disorder instead of chemically reacting with aluminum directly ever. Same atomic behavior explains gallium melting and aluminum embrittlement remarkably well together today. Gallium's unusual properties emerge from identical underlying structural Chemistry principles consistently everywhere. Mercury resembles gallium, yet causes devastating neurological damage through different chemistry entirely. Gallium alloys remain comparatively safe, despite sharing liquid metallic characteristics with mercury. Hard and soft acid-base theory explains contrasting biological behavior between these metals. Mercury ions behave as soft Lewis acids with highly polarizable electron clouds. Soft mercury strongly binds sulfur-containing thiol groups inside essential cellular enzymes permanently. Mercury disables enzymes, causing irreversible neurological damage throughout affected nervous systems severely. Gallium ions, instead, behave as hard Lewis acids, preferring oxygen donors exclusively. Gallium closely mimics iron entering biological transport systems through transferrin proteins efficiently. Gallium nitrate exploits iron mimicry for important medical treatments against certain cancers. Gallium-68 currently enables advanced PET imaging inside hospitals around worldwide today routinely. Biological outcomes depend upon coordination chemistry instead of simple elemental similarities alone. Gallium safely imitates iron, whereas mercury permanently poisons sulfur-dependent proteins instead, consistently. Different ionic hardness completely changes biological interactions and toxicological consequences dramatically everywhere. Final mystery involves gallium's strange behavior while remaining liquid under atmospheric conditions. Liquid gallium strangely maintains unusual shapes instead of forming smooth spherical droplets. Oxygen immediately reacts, creating an ultra-thin gallium oxide surface layer instantly everywhere. Oxide skin measures approximately 1 nanometer, covering entire liquid droplet uniformly always. This invisible skin mechanically stabilizes otherwise highly mobile liquid metal beneath continuously together. Bare gallium possesses extremely high surface tension under ordinary atmospheric exposure conditions. Oxide layer dramatically changes droplet mechanics without altering underlying liquid composition directly. Electrochemical oxidation controls oxide formation using less than 1 volt successfully often. Increasing voltage thickens oxide while reducing effective surface tension nearly completely away. Reversing voltage removes oxide, restoring original high surface tension rapidly again immediately. Voltage switching enables liquid droplets, spreading, contracting, merging, splitting, and reshaping, repeatedly, precisely. Gallium-based soft robots exploit reversible electrochemical surface chemistry for controlled movement today. Reconfigurable electronic circuits similarly depend upon electrically controlled oxide layer behavior continuously together. Electrochemistry, rather than mysterious forces, controls astonishing liquid metal transformations precisely every time. 5 mysteries connect through one central concept involving increasing atomic disorder fundamentally always. Gallium's paired atoms readily separate because entropy strongly favors greater disorder naturally together. Alloy formation further increases disorder, preventing organized crystal formation during cooling processes. Structural disorder enables gallium penetrating aluminum grain boundaries, causing embrittlement from within effectively. Hard acid chemistry allows gallium replacing mercury across safer biological applications successfully today. Oxide formation provides controllable surfaces, enabling innovative engineering and robotics breakthroughs worldwide continuously. Bonding, thermodynamics, diffusion, coordination chemistry, electrochemistry unite, explaining gallium comprehensively through science. Gallium connects multiple chemistry disciplines within one extraordinary element, demonstrating scientific unity beautifully. These mechanisms extend beyond curiosity toward important technological and industrial applications globally today. Gallium compounds support advanced semiconductors, radar systems, satellites, and modern electronics worldwide. Gallium nitride and gallium arsenide remain strategically valuable technological materials internationally today. Global trade increasingly reflects gallium's critical importance for future technological development worldwide. Every mystery ultimately possessed understandable chemical explanations grounded within established scientific principles thoroughly. Apparent scientific magic usually disappears once genuine mechanisms become properly understood through investigation. Careful curiosity consistently transforms confusing observations into meaningful chemical understanding for everyone. Real chemistry rewards persistent investigation beyond superficial explanations and internet myths consistently. Countless periodic table mysteries still await equally fascinating scientific investigations ahead together. Understanding mechanisms always reveals deeper appreciation for chemistry's remarkable hidden complexity everywhere.